So let's work an IR problem before we continue on with some substitution. And again, refer back to some of the notes and handouts you have whenever we do problems up till test number 2, because you will be given the IR values and NMR values, etc. So you can refer to them. They're not tests right now in terms of when we ask you these questions, that you can't look at these cheat sheets. So on your test, you will be given that information. Now for this problem, it's asking me what kinds of peaks do I expect to see, what kind of representations. So the most important representations that I should see should be from my double bond. So I should see a carbon-carbon double bond. I should see an OH. Now, um, am I expecting to see sp3CHs? Yes, but a lot of things have sp3CHs. Um, Should we be seeing sp2CHs? Yes. And if the answer is there, sure. And so this is really like what's here that we can potentially see. So I have a medium peak around 1600. That's where we'll see our carbon-carbon double bonds. Sharp peaks around 1700. That's a carbonyl. So that's not going to be relevant to us. A broad peak around 3200. That will be OH peaks, and sharp peaks around 3400. Those are NH generally, so this is not going to be relevant to us. So our correct answer would be C. So using that information, answer the following question. All right, we also talked about proton NMR before, and this is, you've seen this actually, same exact question, just maybe written differently multiple times. So a proton that is in what position will appear where on your spectra when you have more electron density surrounding it. All right, we also talked about proton NMR, and so there are three main things on proton NMR that you need. You need to know the electronic environment, what term corresponds to that. We need to know the number of protons, so what corresponds with that. And we need to know um, the number of neighboring hydrogens and what corresponds to that. So the electronic environment tells us about our location. So this is our shifts. That is related to our ppm value. The number of protons is on for that signal. That's going to be related to the area under the curve. So this is our integration, which is the area under the curve. And lastly, our neighboring protons tell us more about um, the the shape that our molecule, or the shape that the peak will have. So this is our multiplicity, which is essentially the shape. Okay, so doublet, triplet, etc. So if you're given a problem like this and you have to determine what is the multiplicity, how would you go about doing that? So you would look on all sides. So on this side, I a have a carbon with 3 hydrogens neighboring. So I'm neighboring with 3. Over here, I'm neighboring with none. So I should have n plus 1 equal 4. It should be a quartet. Okay. Don't get fooled by the fact that there are methyl groups here. Those hydrogens are too far away. So we talked about nucleophilic, electrophilic reactions, SN1, SN2. Which one of these would not be a true statement for our mechanisms? Which one of these would not be a true statement about our reactions when we're talking about homolysis and heterolysis. Homolysis means we're going to break and distribute the electrons evenly. Heterolysis, they're broken unevenly. And we talked about SN2 reactions. SN2 reactions are what kind of mechanism and what kind of order for the reaction. All right, so in class we'll spend more time on substitution reactions, but I want to talk a little bit about good nucleophiles and poor nucleophiles, and your worksheet's going to have a long list of these, so please look at them and rationalize them. But a couple of little tips is that it still follows along with the areo. Typically, we don't really care too much about the O part, the orbital part as much for this purpose, but the most important thing is the atoms. So for instance, sulfur being a leaving group versus oxygen being a leaving group, which one of these is bet is actually better at handling the negative charge in terms of atoms? That would be one criteria that we look at. Then we can look at resonance. So for example, here, both of these oxygens that have the negative charge can leave. However, this one would be more stable, and so more stable the conjugate base, or more stable the compound is, the more stable the leaving group, which means it's a better leaving group. So this is a better leaving group. The next thing is if we're talking about induction. So if I were to compare this leaving group versus this leaving group, the fluorines would make me more stable, and so that would be an even better leaving group. So we see when we look at our table that they talk about tosylates and mesolates as good leaving groups, and it's because they have, and triflates, they have very good resonance. There's a lot of resonance. And in particular, this one has not just resonance, but it's resonance and induction. One example of something that will never be a leaving group is carbon. Carbon is never a leaving group for our class. Not in this class we'll ever learn it as a leaving group. We can do alkyl shifts, but it will never just leave by itself, because carbon with a negative charge is so unstable, it's not going to be a very good leaving group. And so when we start talking about this, we'll see that good leaving groups make poor nucleophiles, and poor nucleophile and good nucleophiles are poor leaving. And that's one of the things that facilitates reaction. So if I have a leaving group plus my nucleophile, you want to have a good nucleophile that will stay on your molecule. Otherwise, if your nucleophile is not very good to stay on your molecule, it's just going to keep coming back off, and your leaving group might go back on. So if we look at um, good nucleophiles are oftentimes very good Lewis bases. One exception to the word base when we talk about nucleophiles is that there are certain bronzid-lauride bases that are not really bases. So like halogens, chlorine minus, bromine, they're such poor bronzid-lauride acids in terms of picking back up hydrogens, but they actually make pretty good, just because of electron density, they make good Lewis bases. They're not the most excellent Lewis bases, but they're pretty good and can react. Now again, we can use areo to determine with other than that exception, we can use Arrow to determine what would be good um, nucleophiles. And then again, there's some exceptions, some relating to the halogens again, but that will be on your worksheet that you can look at those and rationalize those. But an example of a good um, nucleophile are things that are very, very, very unstable Lewis bases, meaning very reactive Lewis bases. So for instance, CH3 methyl anions are extremely, extremely strong nucleophiles. They're very strong nucleophiles as compared to something like an OH. So these will react extremely quickly. And so using that same judgment that we have, so for instance, this thing, acetate, which some of you had on test 1, is actually a very poor nucleophile. It's a poor Lewis base. Even though it has a negative charge, because of resonance, it's not very good. So when we look at those things, you want to look at your handout and use Arrow to help justify. So in terms of substitution reactions, we have to be concerned with stereochemistry. So before we step into stereochemistry, in terms of SN1 reactions versus SN2, um, based on the mechanism, based on the fact that we have to form carbocations in SN1, the more stable carbocations are going to be more likely. So tertiary carbocations can react, secondary carbocations, but you're never going to see primary or methyl carbocations doing SN1 reactions. We may also see stuff that have resonance as well undergoing because they're actually going to work very well. SN2 reactions, on the other hand, and we'll talk more about this in class, because of sterics, are better with methyls, and then primary is next, then secondary, but tertiary pretty much won't work. So that brings us to then what happens in terms of stereochemistry. What if I have a molecule that has some sort of stereochemistry? Now, this is not going to make a difference with methyls on primary because there's no stereochemistry, but what if I had a molecule like this? You had your leaving group, you have a chiral center here, remember you have an understood hydrogen, and you're going to do an SN2 reaction. Now, when the nucleophile comes in, it has to come in behind the leaving group. Why? Because there is some sterics. Even though I drew the nucleophile here, the nucleophile can't come in and attack at this electrophilic center on the same side as the nucleophile just because of sterics. So what does that mean? What it means is my molecule would have to have the nucleophile attack in this orientation opposite to the leaving group, which would then mean that where our nucleophile will be added will be opposite, will be the inverse of where the leaving group was. So in terms of stereochemistry, we get what's called inversion of stereochemistry. So this only plays a role if you have a chiral center, right? This only plays a role if the molecule that you're forming had a chiral center that you were attacking to begin with. If you didn't, then this is not an issue. For SN1, my first step is to form a carbocation. So my leaving group leaves first and you form a carbocation. So in this case, the formation of the carbocation, this stereochemistry is essentially not significant anymore because now, because I have a carbocation, carbocations are trigonal planar, meaning flat. So in terms of where the nucleophile comes in, it can come in on the top face or it can come in on the bottom face. It can come in from either side of that MTP orbital. And because of that, you get what's called a racemic mixture. So you can either get the nucleophile on the top or the nucleophile on the bottom, so you get an equal amount of the enantiomers. So which one of these would make the best nucleophile? Based on what we talked about before, there was one in particular that I said would make the best nucleophile. So in terms of the SN1, SN2, here's a quick little summary and review, and I'll talk about how you know when something's SN1, SN2, etc. And then we'll move into um, next time the elimination reaction. So SN1 reactions, like I said, are unimolecular. The rate of the reaction only has to do with the substrate. So that's the first order in respect to the substrate. And the reaction uses a polar protic solvent. And I'll mention what those are. And we'll talk about why that is another time. The best nucleophiles are in this order, so benzylic and allylic about the same, then tertiary as well, then secondary, then primary, then methyl. Pretty much primary will never happen and methyl will not happen. You need good leaving groups, and poor nucleophiles are okay because our first step really depends on the leaving group. SN2 are bimolecular. We're going to be second order with respect to having first order with the substrate, first order with the nucleophile, so that's a second order reaction. It is going to use polar aprotic solvents. Now, one thing that's kind of weird about this is that the benzylic and the allylic, depending on the sterics of it, are actually better um, than some of the other ones that other groups that you might have. And so tertiary is the worst, secondary, and then primary. And the benzylic and the allylic can depend on sterics. So if it's very sterically bulky, it's just as bad as tertiary. If it's not sterically bulky, it probably is just as good as primary. Poor leaving groups are okay because we're not dependent on the leaving group leaving first. Now, it can't be impossible leaving groups, but you can have weaker leaving groups, but you have to have good nucleophiles because the nucleophile has to attack. And these reactions are slower because of steric. So why would someone want to use these um, leaving groups? These are some of the best leaving groups that you can have. And we haven't really seen these up till this chapter, but these groups, so tosylate, which we abbreviate TS, mesylate, which we abbreviate MS, triflate, which we abbreviate TF. So this is triflate, this is mesylate, and this is tosylate. And so there's resonance that is associated with having that sulfur with those double bonds. Here I have a lot more because I can do resonance also from the oxygen through the ring. Here I have some induction going on here. So this is not the best of them, but you still have resonance. The thing that this adds is that it's small. So even though the tosylate and triflate are really good leaving groups, the mesylate's just smaller. So if you need something smaller, that's why you would choose that one. And oftentimes we can replace the OH group on our molecule for it. So if you have OH is not a great leaving group. Essentially, we can take the oxygen I'm going to put the oxygen in blue, and I can replace that hydrogen that was on my OH group with the tosylate or the triflate. So the oxygen stays there, and this is important because if I'm talking about stereochemistry, replacing the OH with the tosylate or the triflate doesn't change the stereochemistry, only because I'm not actually taking off the oxygen. I'm just adding the tosylate or triflate onto the oxygen. I'm really just replacing the hydrogen, and that's not going to change the stereochemistry. Oftentimes when we do these reactions, you do them in pyridine with tosyl chloride, mesyl chloride, etc. And so how we would do that is, let's say you take your alcohol, you would react it with the tosyl chloride, and the tosyl chloride just means that there was chlorine here instead of a negative charge on this oxygen. So chlorine here, chlorine here. We'd oftentimes do this in pyridine, and we abbreviate pyridine as PY. And the pyridine is just to help remove the hydrogen because pyridine is the base. And you would get this thing. And this part's not the important part. So in terms of solvents, solvents serve a couple of important roles. And one role for the substitution reaction is that it can help to stabilize leaving groups or nucleophiles. So in particular, stabilizing leaving groups, we have a polar protic solvent here. Polar protic just means that it's polar, but protic meaning it has a hydrogen on the solvent that could do hydrogen bonding. So can hydrogen bond. So not just because it has a hydrogen, so it's not protic because it has a hydrogen, but it's a hydrogen that can hydrogen bond. So here we have a hydrogen bonding effect with an ion, and if I have a leaving group and it comes off, and I can do this intermolecular force, I'm going to actually make this more stable. And the more stable my leaving group is, the more likely it is to come off and be stabilized, right? So in a polar protic solvent, so this is methanol, for example, methanol stabilizes my leaving group. So if I had a reaction like this, and the leaving group came off in my SN1, the polar protic solvent helps to stabilize that leaving group. Okay? And by stabilizing that leaving group, it makes it more likely or easier to leave. So some examples of polar aprotic solvents that we would use for SN2 would include something like acetone because it doesn't hydrogen bond, it doesn't have OHs or NHs, DMF, acetonitrile, and DMSO. Now, in the next slide, I'll talk about some things that affect nucleophilicity, but one thing that I want to mention is that we use our aprotic solvents to help to stabilize, the protic solvents to stabilize leaving group, but we don't use protic solvents in SN2 because protic solvents in SN2 will also stabilize nucleophile. So what we're trying to avoid is stabilizing the nucleophile too much because in the SN2, the strength of the nucleophile is very important. So these solvents do not hydrogen bond with the nucleophile, so it doesn't weaken the nucleophile. And so by surrounding the nucleophile and hydrogen bonding, you're actually stabilizing it more. And so we don't want to do that in SN2. Now, when we talk about our order of stability of nucleophiles or reactivity of nucleophiles, there are different orders that we can look at, and you'll see that on the next page. But what I want to point out is your solvent can actually reverse the predicted reactivity or stability of our nucleophiles. And I'll show you that in the next slide. But by having a nucleophile in which you're using a polar protic solvent, that can help to stabilize a nucleophile more. And so typically, some nucleophiles are better at being stabilized than others. And by doing that, I can change the reactivity of my nucleophile. And so one place that we see this is in the halogens primarily. So as we look at our halogens, and again, you'll see this on the next slide, I can reverse the order of reactivity of my halogens based on the solvent that I choose. So if I choose a polar protic solvent, I can get um, them to be one way. If I choose a polar aprotic solvent, then they can behave like they normally would by predictions. So here's a summary of some of the factors that affect nucleophilicity. So charge, more charge, the better. And actually, these are the same factors that affect leaving groups, but just the opposite. So if you have a charge, that actually is more likely when you're talking about the same thing. We're not talking about including resonance or anything like that. Like if there's no resonance included, then and it's just solely charged, then that's the case. Electrophilicity, the more electrophilic something is, the better it is at being a nucleophile. Like I said, solvents can reverse the order. So polar protic solvents will reverse the order of behavior of the nucleophile. Um, protic solvents, aprotic solvents are not going to do anything. So the polar protic solvents are going to be better at um, these reactions. Bulky nucleophiles are actually harder to work with, so the more bulky something is, the less nucleophilic it is. One of the last things that we'll talk about is protonation. So sometimes you have a leaving group that you could potentially protonate, and by protonating it, it actually will make it a better leaving group. So for an example of that is alcohols. So other than making alcohols into tosylates or triflates, which are actually the best thing that you can do, we can protonate the alcohols, make them into better leaving groups so that when the alcohol leaves, it leaves as water instead. So having your OH leave as OH minus versus water, the water is better. So here's a quick just little summary, and we'll go over this in class. Um, the only time we care about our substrate in determining SN1 versus SN2 is secondary because that's the only one they really have in common. Um, First, you evaluate the nucleophile. If the nucleophile is a weaker nucleophile, then it might go SN1. If it's stronger, it might go SN2. We evaluate our nucleophile, our electrophile. If the nucleophile is kind of middle of the road, um, the better the nucleophile, the more likely it's SN1. The okay nucleophiles or more bulky nucleophiles are going to go SN2. Um, when we have, if everything is kind of similar, then we can look at the polar protic solvent. So that's kind of a clue, but it's not. Let's say if you have a primary carbocation and you use a polar protic solvent, that's not going to change that this becomes SN2 to SN1. This is really only when we're talking about secondary.